Hey, welcome everybody to our bsac weekly seminar. Today, as we did last week, for any of you who were here last week, we have a bsac alumni person that's joining us and relaying maybe some of their experiences when they were here and how they, in this case, started a company and kind of went from there to where he's at now. But this is Richie, I guess he goes by. It says Richard. Anyway.
Either one's fine.
Yeah, who is the Senior Director of Engineering for the Smart Sonic Time of Flight product line at TDK, or TDK-InvenSense. And his team there is responsible for MEMS, CMOS, and software application development for the chip-scale ultrasonic transceivers that he co-invented. So he'll be telling us about that and how we got started. He joined TDK-InvenSense through the acquisition of his startup that he co-founded called Chirp Microsystems. You might have heard about that. And therefore he started that company based again on his research that he did here at Berkeley, where he created ultrasonic transceivers, which we'll hear about. He has 25 patents, 4 journal articles, conference papers, et cetera, And with that, I will go ahead and turn it over to Richard.
Thanks, John. Thanks. Happy to be here. So I wanted to talk about the journey that me and my co-founders and my colleagues have been on for the last about 15 years now, working on air-coupled MEMS ultrasound. I called my talk "Follow the Signal" because I felt like that for a lot of times that was kind of my job, to kind of follow where the signal was going, through the MEMS, through the ASIC, through the software, and make sure, we were measuring the right thing. So let me talk about. Click on my screen there. Let me talk just kind of visually the history of the project I've been working on. We started here in bsac back in 2008, before there was the Swarm Lab. We were working on, at that time, making these ultrasonic time of flight sensors that I'm going to tell you about here in the Berkeley clean room, and with partners to do some of the depositions. I'll talk about the 5 years that we spent here in UC Berkeley developing the technology. Then I'll talk about the almost 5 years that we spent as an independent company, Chirp Microsystems. And then the last about 5 years spent inside TDK, developing the technology further, getting the sensors to mass production, and spreading out across different applications that can be addressed by the same sensors. Yeah, and here in the middle, we moved to our office in West Berkeley, so we're still here in Berkeley. So that's the outline of my talk. We're going to talk about my time here at Corey Hall, the time in the startup, joining TDK. I put a section in about some patents, the importance of IP, and also some kind of key patents that we got over the years. I thought that might be interesting, and it's an interesting way to share with you all because patents are public, but without any NDA problems. And then a couple ideas for future work in the area, kind of related areas. So the technology, you'll see the technology is based on aluminum nitride as a piezoelectric material, and the important thing to acknowledge is aluminum nitride is in all of your phones. It's like wildly successful, commercially successful, at being used for FBARs, which are filters that can be used to like channel select a certain frequency band for your for a radio signal, right? And so many years ago, SAW filters were used in phones, and much of the early work on SAW filters came from Berkeley. But starting in like the mid 90s, FBAR was invented at HP Labs. and went through, basically took over the channel select filters for for wireless connectivity. And the interesting thing is, like, FBAR is such a wild commercial success that now Broadcom, which is like with a market leader, is worth 8 times what HP is worth today. The technology having come out of HP. So we use this same material and some of the tools developed to make these filters to make aluminum nitride piezoelectric micromachined ultrasound transducer. And the way the technology works is we have a layer that is a piezoelectric layer that's sandwiched between 2 metal electrodes. There's another layer that it doesn't matter so much what material it is, but it's acting as a binding layer. So when we apply a voltage between the top and bottom electrode, the piezoelectric layer expands, and the binding layer will cause the whole thing to move out of plane. And it's a linear actuator, so if you apply the opposite voltage, it moves the other way. And you can then make a resonant device that's going to resonate at a certain frequency. It's going to move in a trampoline mode, and it's going to launch ultrasound waves into the air. So our early devices were 190 kilohertz up to 220 kilohertz. At that frequency, we could get a bandwidth of about 6 kilohertz at the time. And here's a picture of one of the devices. This is probably from about 2010, 2011. So we started using these devices to build ultrasonic rangefinders. And so there's a single PMA in this board here that's shooting sound out through the back of the wafer, through the back of the chip, and bouncing off this target. And back then we were, as today, we were doing a pulse echo range finding. So we send a pulse of sound, we wait for it to come back, and we measure how long it takes for it to come back. And that's the range to the target. So you can see here like an early, like a peak in the signal where the target is. So that's the reflected signal from the target. And so this first rangefinder had about 0.5 meter range. It was using this 190 kilohertz PMA. We also built pitch catch systems where you have one ultrasonic transceiver and another, and you send from one to the other. And this ended up being a key application for us later on. But the very first one we built was very simple. It just had a transmitter on one side and then a receiver on the other, and it was connected by a wire. So there was no real synchronization required, but you had a wire telling the transmitter start transmitting, and then at the same time the receiver would start receiving, and we'd measure the time that it takes for the pulse to travel across. And so there's a video here. This is from Sudarjadai Hall. We probably won't watch the whole thing, but you can see here I'm gonna move it in a kind of a sinusoidal pattern, and it's measuring the range between the no. Oh boy. Let's see. Okay. We're not going to report the problem to Microsoft. Okay. There it is. Okay. So now we're not sharing the screen. Is it looking okay? Okay. Okay, sorry about that. I had too many PowerPoint windows open. Yeah, the funny thing about this is how much hair I have and how young I look. So this shows you how long I've been working on this project.
Is it the project or the startup?
Yeah, I think it's the kids actually. My hair was fine until I had kids. Yeah, at that point we seized on the idea to make an array of ultrasonic transducers so that we could measure not just range but also the direction to a target. And so at the time we built a printed circuit board that had transmitter electronics and then multiple 7 channels of receive electronics on it. And then basically went into LabVIEW and we did the processing, on the computer. And so, we were using this array chip. We were using a linear array of receivers and a single transmitter, separate transmitter. And these, the element spacing here was about half a wavelength, which is 0.9 millimeters. So we're still operating at about 200 kilohertz. And so the way this works is when we get an echo back from a target, and let's say it's a hand and it's a little bit off center of the array, there's going to be a delay between the elements in the array. So the receiver that's closest to the hand is going to get this wave that arrives first, and the next channel is going to be a bit delayed, and the next channel will be a bit delayed from there. And so we're going to take those 7 signals in this case and try to combine those into a 2D depth image that's going to give us the range and angle to the target. And so if I just look at a single point along these waves and I add them all together, you see here that the waves are out of phase. So they're going to add together to something that's sort of close to 0. Now, when I shift the waves along, sorry, I need to wait for my animation to move. As I shift the waves along, when they line up, I'm going to get a peak. And then, when they go out of phase again, I get less when I add them together. And so we do that for each range sample along the trace, and then we get something here that is going to be tell us where the peak in the range and angle is. So the color here representing the amplitude of the beamformer output. Yeah, 2012 we made this 2D rangefinder, and yeah, you can see the echo there. We're seeing the echo from my 2 hands and my head. And there's a video of basically the same thing. You can see all the wires going into the LabVIEW box, the National Instruments box there. So then sort of the last part of my PhD, I built a CMOS front end for this array. And so this was a 180 nanometer high voltage CMOS that had so the circuit on the chip is in blue here. It had a high voltage transmitter and the transmit and receive switch to basically isolate the high voltage from the low voltage receiver, and then a front end and a 4th order bandpass sigma delta converter that will digitize the signal and basically provide a 1-bit output of the of the echo waveform. Okay, and then all of the digital processing was off chip, and so this part here would basically you feed that 1-bit data into demodulator that will do an I and Q demodulation of the data and filter it and then put it into the beamforming process that I mentioned before. And so the beamforming process is actually done in the I and Q domain, but the idea is the same. You know, so then based on that chip, we built a gesture recognizer demo. And so that chip is down here on the green board and the array is on the blue board. And you see this is just going to detect right and left gestures, able to kind of flip through my Hawaii pictures here. Okay, and so this is basically where we were when we graduated and decided to go off into the startup world and see what we could do. Yeah, so the next part of my talk, I'm going to talk about the the startup phase. The Go West Young Man is actually just my joke, because we actually moved our office only like to the west side of campus, and then we moved again further west, but we're still in Berkeley. So some of these slides are actually from that time. This is like some philosophical slide. I was trying to think about, like, people are like, well, what is FedEx? Well, FedEx is a company that moves stuff around, right? So what it was, Chirp was like a know where things are company. So we're trying to help your device know what's happening around it, right? In a like a low power way that's using sound instead of light, right? And what we found as we went along is like we have there's a lot of kind of layers between the sensor that goes in a phone and building an iPhone, right? And so when you're working with some customer who's going to incorporate your device, they don't necessarily want to understand like what is ultrasound and why is this happening when I test it this way. They just want something that works, right? And so what we found out is we need to provide like solutions that like solve a real problem, not just this kind of funny chip that emits sound, right? And so don't give the customer a hammer, don't give them a chip and say, well, you can figure it out. We have to like build them a house. We have to give them a solution that says, that answers their problem. Is somebody present in the room, or is there no one there? That type of thing. I'm just going to talk just very briefly about fundraising. We were like a very kind of capital light startup. So we did try to like go to Sand Hill Road and meet all the Kleiner Perkins and on down, but at least at that time the investment in the hardware sensor company, it was very hard for them to see the business case for making a big investment. But we were able to raise quite a bit of money from we did eventually raise money from institutional investors, but we were also able to raise quite a bit from grant programs, including the NSF SBIR. This is a great program for anybody starting a small business. And then we also had some grant through the California Energy Commission, where we were working with folks on campus to build an anemometer. And around this time, we were still working heavily on the arrays. This is kind of a video showing our the kind of peak performance of our 2D arrays. So we had 2 arrays. They're shaped in 2 lines, and each of them had 10 elements. So this is 20 PMUTs. And so right now you can see this is like a top view, so looking down on my hand, and this is like a side view, so looking across. So you see that it can kind of recognize the pose that I'm making with my hands. I'm clapping right now. And now this is like sorry, let me just reset it. So This is like a 2D or a 3D view. So the color is encoding how the depth. So you can see my fingers are here in the front and my body's in the back. So you can see it it can detect, it has enough resolution to see my finger pinches from, maybe a third of a meter away. So the array stuff was great, but it was like not obvious how we were going to get that into a phone or a tablet or some kind of consumer electronics. And meanwhile, people were telling us, well, we could use just one of these things to detect when you hold your hand up, your phone up to your head. And if you have black hair, sometimes the optical sensor doesn't detect it. And so what if we use sound instead? So that's where we saw like an opportunity to build a single element device that can detect, you holding your phone to your head. So we built a little demo based on that. And that was, integrated into a Nexus 5 phone with some help from some Singaporean friends. And, it worked. There's a video here. I'm not going to play it, but, it was able to detect when you put it up. We could even do some gestures with it. Well, I am going to play it, I guess. So yeah, you can see there's a gesture. Based on that, we were able to define our first product, which was CH101. So this has a PMUT that's off chip and an ASIC that I'm showing here in the block diagram. So the ASIC is built around a small processor that's on the chip, and the processor is able to control like a bank of registers that control the other peripherals. And so the processor is basically able to control how the device is going to take a measurement. But while the device is actually taking a measurement, the processor is going to be asleep. So what it's going to do is it's going to configure a state machine that's going to keep track of the ultrasonic measurement while it's in progress and in like a kind of cycle accurate way. The state machine is first going to control a transmitter to create a high voltage square wave, basically, to drive the PMUT for a certain duration that's programmable. And then when it's done transmitting, it's automatically, the state machine will automatically turn on the receiver and execute some instructions for the receiver, which are basically how long should I receive and which gain settings should I use. And so it's going to do all of that autonomously. The receiver will take the current coming out of the PMUT and amplify it and put it into an ADC. The ADC very similar to the same one used in my Ph.D. And then there's a mixer and a filter on the chip. That's a digital, so the ADC is making a digital 1-bit signal, and the mixer and the filter are in the digital domain. They create these I and Q samples of the echo and put those directly into the data memory that's on the chip. And that whole process is happening without the processor being involved. When it's done receiving, then it will generate an interrupt to wake up the processor, and the processor can decide whether to run some algorithm on the data or just send the data out, tell the external host to read the data out. Yeah, here's a die shot provided by our friends over at System Plus, who like tearing down interesting technology. So you can see some analog section here, and then you can see the place and route over here. These very regular sections are the SRAMs. It's kind of a picture of the productization, including the packaging. So 11 years ago, we were we had something this size that kind of used a PC to run it. As we became an independent company, then that's when the push really came to shrink everything. And, you know, in the end, we came away with a CH101 in a package that's 3.5 millimeters on the side. Here's another picture of the CH101 cut in half by the System Plus folks. You can see how the package is constructed here. So that the sensor is placed right over an acoustic port that's on the top of the sensor. And so we have sound coming out the top. And then the ASIC is down here and they're connected through the package. So this is basically a fancy microphone package. And you know, then all of the analog business happens on the ASIC, and the ASIC has a digital interface to the outside world. So overall, you know, Chirp was, including the university phase, about 10 years in, when we sold the company to TDK. During that time, we spent, you know, on the order of $10 million on R&D. So in the remaining time, I'm going to talk about what we've done since then, how we kind of fanned out the tech to different applications, and a brief talk about patent. Looking at time, we'll have a brief talk about patents, and then maybe a few minutes for like kind of interesting research directions that I see. So the first point I want to make is a lot of disciplines really come together to make an ultrasonic time of flight sensor. You know, if you think about, I showed you the package just now, that's down in there. There's a whole bunch of design work that goes into there. There's a whole bunch of, you know, product engineering, test engineering, firmware and software development that goes into the chip itself. But then also important is what goes around the chip. And so since we have an acoustic device, we have to get the sound, you know, out of the customer's product out to whatever we're trying to sense, whether that's a hand or a wall or a floor, and you know, back to the sensor. And then also there's a big software component that runs off chip that basically takes our sensor and, you know, provides a driver that customers can use to like customize the behavior to their needs. And then on top of that, you have all of the kind of supporting things that you need to make a business. And so when we became part of TDK, this was like a great opportunity for us to leverage, you know, the great know-how inside the company about how to make, you know, how to make sensors, particularly in TDK-InvenSense, and, you know, how to sell them and how to distribute them, right? The other problem we saw was that the startup silicon that I just talked about kind of had some shortcomings. So one of the things that I've spent the last couple of years working on is a new ASIC that makes it easier for our customers to use our tech. One of the things we did is we put a lot more compute on the chip so that we can do a lot more algorithms baked into the sensor, so that everything's, you know, compartmentalized, and you know, you have a sensor that can really detect if a user's present in a room, you know, without any external processing. There's you know, several new features in this ASIC, including, you know, faster I/O, 3.3 volt I/O. We've learned that in the IoT world, a lot of things still run on 3.3 volts, and so it's important to support that. And so now we have our, you know, our startup silicon sensors that launched 2019 timeframe, so about a year after our acquisition. And then we've recently launched our next generation that's using the new ASIC. And so these products are available. You can buy them on DigiKey even. If anybody in the room wants to play with them and doesn't want to pay, for our eval kit, you can send me an email. I'll see what I can do. We are also working on a new long-range PMUT. So this is to address a need seen by our market to basically be able to cover a room maybe almost this size with a single sensor to say whether somebody's in the room or not. So this room may already have some proximity sensors, PIR sensors to detect when we come in, but being able to do that with ultrasound would lend some important advantages. With PIR, sometimes you sit too still and it will see that you're gone. Certainly with ultrasound, we can have that problem too, but we're sensitive as you walk towards the sensor, whereas PIR is sensitive as you walk across the field of view of the sensor. So there really are complementary technologies. One of the ways we were able to extend the range of this device from up to about 9 meters to a wall is that we moved to lower frequency. And so you have lower ultrasonic absorption at lower frequencies, and sound just travels further. But we've also made significant design improvements, including differential actuation of the PMUT and design changes of the actual membrane. Now a couple slides to talk about our customer application development. So our first product, CH101, went into a product called the VibeFocus Plus, which is a VR headset with 2 controllers. And our technology is used to track the position and orientation of the controllers while the user's wearing the headset. And so there's 6 of our CH101s on the headset and 6 of them on each of the controllers in the ring. And we also developed a sensor fusion algorithm to fuse the ultrasound data with the IMU data so that you have very smooth tracking. So the accelerometer and the gyroscope and the IMU are basically providing your fast update, and the ultrasound is providing like the position reference. So this was like an application where customers were basically banging on our door back in 2016 saying, we need some solution to this problem. And it took us a couple of years to develop the solution and get it to market. Around the same time, Oculus and what became Meta were working on the same idea, but using computer vision. And so actually you see today, if you buy a VR headset, it's almost always going to be computer vision. Ours has some, nice advantages like lower power consumption compared to the computer vision, but it turns out VR headset, you got a couple of displays, you don't really care. So, but this was a great starting application for us, but we knew that we had to be quick and that it wouldn't last forever because we knew computer vision was catching up. Since then, we've fanned out a lot across different markets. Robot vacuum cleaners is an interesting one for us right now. There we're detecting the type of the floor underneath the sensor. It's the same CH101 sensor that's used in the VR controller tracking, but it's just measuring the echo from the floor a couple centimeters away. If there's a strong echo, then you have a hard floor. And if there's a small echo, you have a soft floor. If there's no echo, you're on a cliff. And so, you don't want to drive the robot off the cliff, and you don't want to mop the carpet. So this is actually like a pretty simple application, but we, certainly a lot simpler than the controller tracking, but it's been quite successful. We're also seeing smart locks as a big focus area. Smart lock, it's also a simple application. When you walk up to it, you want to turn on the smart lock and take a picture. And if the picture matches the person who lives in the house, then you unlock the door, and otherwise you send a notification to the owner of the house. And so these smart locks are quite popular in China now, and our sensors being used for the low power wake up. So it's basically the only thing on, and you walk up to it, it turns on the application processor, which is going to take the picture we're also doing presence detection in laptop, in like wireless speakers. We had this project for contact tracing in 2020. Our customers, again, were banging down our door. We need to know when people are closer than 8 feet away. and actually developed a solution, and basically they were close to going mass production when the vaccines were announced. So timing is key. This is just a block diagram that explains how the smart lock works. Basically you'll have CH201 being the only thing on in the system. Everything else is turned off. CH201 has an algorithm loaded on it that can detect when something's moving in front of it, and it won't detect like walls. So it has what we call stationary target rejection. So it's only detecting somebody moving. And so when it does detect something, it wakes the rest of the system. The system takes a picture and sees whether it should unlock the door. So I am running short on time, so I will just talk about patents briefly. I think most of you probably know what a patent is, but it's actually a pretty fancy thing, because it makes you it gives you a legal monopoly on a product, where you can sell that product, and if someone else tries to sell something very similar, you can use the government to block them. And so patents are important, way to protect our business. And the other important point is that our business was started by licensing patents from UC Berkeley. So we made some inventions while we were here, and UC Berkeley filed those patents, and then we were able to license them from UC Berkeley. And so I encourage you, if you do have some idea that could be patentable, to try to pursue it, because not only could it lead to some kind of spin-off, but you also can get royalty payments from the university if your patent is licensed by someone. So yeah, I have so this is an example of a patent that we licensed from UC Berkeley. Is on how to find the frequency of the MEMS by listening to the ring down current after we transmit. So when you transmit, you get the MEMS vibrating, and then when you stop transmitting, it will keep vibrating for some time. And by listening to that ring down, we figure out if we have a frequency error between the frequency that we're driving the MEMS at and the frequency that it wants to move at. And so that's like one of our key inventions that we licensed from Berkeley. I have some more here that I'm not going to go through because we're running out of time. Yeah, just briefly, I wanted to kind of leave with a few ideas about related topics. I ultrasound can also be used underwater, but radio doesn't propagate well underwater. So there's been some interesting work done creating ultrasonic links in the body, but it could also be done over longer ranges, creating ultrasonic links for steering robots, transmitting data back from the robot underwater. Then you see me talk a lot about single pixel ultrasound and about the array work we did here, but it would be also interesting to look at creating more like several different frequency ultrasound transducers to improve the bandwidth of the echolocation, and so then you can make a very precise ultrasonic transceiver. Yeah, I have some other video of finger tracking. Then I think there's also interesting opportunities around sensor fusion and machine learning related to ultrasonic processing. So we did some fusion that I mentioned about for the controller tracking, but it's also can be interesting to look at fusing IMU data and ultrasound to help robots navigate around the world, particularly in places where you don't want the video camera there. Machine learning in general is just really good at processing sensor data. But yeah, today most of our algorithms are designed by a Ph.D. Algorithm engineer. I think there's a lot of interesting work still to be done at basically taking the ultrasound data and feeding it directly into a machine learning algorithm. I didn't talk about sensing air motion with ultrasound, but that is another application for ultrasound. Basically, rather than measuring how far away something is, if you know the distance between your ultrasound transducers, then you can measure something about the air in the space. You can measure the air motion, but you can also measure the temperature of the air and even the humidity of the air. This could be like an interesting way to make a very precise sort of weather station. I'm gonna finish my talk there so I can leave time for a few questions. I want to acknowledge all my colleagues that I worked with over the years, and thanks for coming to my talk, and happy to answer any questions if you have them. Yeah.
I saw a slide with your roles over there.
Oh, sorry. Yeah, I decided to.
Different from,
Yeah. I kept this slide in here because I thought it was interesting. Just to kind of show how I've gone from, so 2013 I graduated, and we've done several tape outs over the years, and so tape out year is always like kind of a year where you don't remember seeing your kids, or you don't remember seeing your apartment. yeah, recently I've become like more of a middle manager. So, my role is continued to kind of change as the as the years go by. But um,
Something else is, in your PhD, you saw that, with gesture recognition. Like a lot of things with just
yeah,
sensors, how is that?
yeah. I think when we spun off, we thought, okay, Samsung had recently launched a phone with some kind of basic gesture recognition. We saw, okay, well, maybe the market's going to go towards interacting through gestures. We didn't really see that take off much. There was some interest in like car sort of audio control, but never went too far. And then it also seemed really hard to get the array integrated into a device like a phone or even a robot, because you have now like a linear array, so it's quite a big slot, quite a big opening where the sound has to come out. And then there's like more challenges on the technology side. Like you need to kind of match the elements across the array, and so we figured like, okay, it's going to be hard enough to make a single one, so save the arrays for later. And so yeah, I mean, I think we could come back to the arrays at some point, but that the key question is like, can you open a slot in a consumer device for the sound to come out? Because you need to kind of maintain the phase of the wavefront as it's coming back, so it needs to have like a wide opening. Yeah.
You had mentioned briefly that the design of the membrane itself, iterations.
Yeah.
Could you speak to those, or is that all proprietary?
Yeah, let me so we do have some yeah, this is basically the best. So yeah, there are pictures on the internet you can see of this device. There was a lot of design that went into basically with the aluminum nitride. The key problem is that across a wafer you get like a wide distribution of stress. So at the edge of the wafer you might have like very compressive stress, in the middle you might have tensile stress. So that's going to make the frequency of the membrane change a lot over the wafer. And so a lot of the design work is how to manage that stress and make it less sensitive to the aluminum nitride stress. So we have some patents around that. I don't have it in the deck, but you can actually, it could be in the backup. There is a picture of the design that basically, yeah, there it is. Yeah, so you can see here, this is again from our friends at System Plus. You can see here's the piezoelectric layer is basically where the spider legs are, and the white area is just a membrane, just a bending layer, but no piezoelectric, no aluminum nitride. And so this design helped basically make the stress of the aluminum nitride less important for the frequency of the device.
Yeah, so I saw on the slides you were on about when your ASIC years were.
Yeah.
What was your schedule for MEMS tape-outs and fabrication like? What devices did you work here at the Nano?
Yeah, so I've always been like on the system side. So my one of my co-founders, Stefan, and he and Andre, they were working in the Nano Lab here. We then went overseas to a fab partner that was not suitable for mass production, but like could actually produce the wafers to get us to the kind of the next level to where we could engage with a fab partner. So here's a picture on the slide. You can see down in the corner. It has another, here's our logo. Here's another logo. So it's fairly open secret who our fab partner ended up being.
Was this the long-term large-scale fab partner?
Yeah. So ST, one of the biggest MEMS companies in the world. Yeah. Not sure. Yeah, not sure that one's public. It's probably old enough. Yeah, maybe. Yeah. Ask me after the. Yeah. Yeah.
Like from the system level, what's the key challenge you see while keeping shrink the system size? I saw you have like 5 to 6 versions of the system.
Oh yeah.
No, I repeat the question.
Yeah.
So the question is what was the key challenge about shrinking this size? Yeah, and I showed a picture. I think you're talking about, it's further back than I thought. You're talking about this. Yeah. Yeah, I think it's actually a lot of engineering work. Meaning just you need like the team, the team that made this was basically me. Except the transducer was made by Stefan and Andre and Dave's team in the NanoLab, right? And so to get then by here we had maybe 5, 6 engineers working on this, and this is still this is still my PhD silicon basically. Then by here we had productized we had made our real ASIC, our product ASIC, and so that took all the digital processing that was off chip and put it on chip, and so that was like another key, a lot of work basically just to make that tape out. Yeah.
On the backup slide, if you skip the feedback forecast, ask for that to develop as like short.
Oh, okay. Yeah. This was kind of the science. So I skipped over the science ideas. Yeah. Yeah, this is just like some interesting idea that's been bugging me for a long time. So if you have like a spark plug, it's striking a spark, which is like a plasma, and the front of the plasma is moving like faster than the speed of sound. So you get a crack. You get like a broadband, basically, shock wave. And so the question I had was like, could you make something exceed the speed of sound with MEMS? It sounds hard, but I don't know if anybody's ever tried it. Yeah. So yeah, and then I looked like 10 years ago, and yeah, our sensor was moving like a meter a second. It moves a few microns and high frequency. So, a couple orders of magnitude, maybe it's possible.
But this is your current project.
Oh, this is my project now? No, no, yeah. They don't let me work on things like this. So that's why I have to, suggest some bright young minds.
So on the right-hand side, it only has a couple of boxes. Customer interface.
Oh yeah.
Building.
Yeah. I'm looking for jobs. Yeah. So thanks for coming.